Okay, so hopefully by now you have a pretty good feel for what a queue is and how you might use it. Um, so now we're going to talk about possible ways that we could implement a queue. So kind of going under the hood here, the way we have been, right? Even though there's already an STL queue class that we can use, we are going to talk about different ways that that class might be implemented. In the text, the first thing that they talk about is implementing a queue by using another class called list. And you probably need to go over that on your own at some point, but um, I'm not going to talk much about that. I'm not going to talk about it at all, actually. um, but I don't think there's too much to it. I think you should be able to, in fact, there's one paragraph about it, and then the rest is just code, right? So I think you should probably be able to figure that out. Let's talk a little bit about a link-based implementation. So, hold on a sec. I'm hoping that the diagrams here, I'm hoping that it's fairly easy for you to see that and kind of translate that in your mind to how that might look in code. So, take for example our sequence class. We had a head pointer and a tail pointer, right, in the class, as well as a couple other pointers. That's basically the same idea we have here, right? The class called linked queue is going to have these two data members, a front pointer and a back pointer. The front pointer is going to point to a linked list that's going to represent the queue. And it's going to actually point to the element that is at the front of the queue. And then the back pointer data member will point to the element that is at the back of the queue. So a linked list works really nicely for a queue. It shouldn't be too hard to imagine what the operations might look like. So the push operation means we're just going to add a node to the end of the list, right? So it might have something like back pointer, arrow next, points to the new node we create, and then move back pointer down. That's probably down here someplace, right? Right, so here, adding an item to a non-empty queue. Create the new node, make back pointer arrow next point to the new node, and then move back pointer so that it points at the new node. All there's to it, 3 steps. You can imagine that popping, so the function called front is just going to return front pointer arrow data, right? The function pop is just going to move front pointer down 1 to the next node. So front pointer gets front pointer arrow next. There will be some memory management issues there, of course. We'll have to delete this first node. But let's take a look at that. So here's the steps for popping. Again, the text is calling it DQ. We're calling it pop. Although actually, to be honest, I don't remember what we call it in the assignment. We may call it DQ in the assignment. So you'll just have to get used to being able to switch back and forth. But pop, DQ, same thing. So we're going to set node to delete pointer to the front pointer because we're going to have to delete that node, right? And then the important part, well, the part that matters even aside from memory management is we're moving front pointer down 1. So front pointer gets front pointer arrow next. Step 3, to be honest, I don't see the point of setting this to null pointer. We're never going to use it again anyway. The important point here is we're going to delete node to delete pointer. Okay. So that's basically it for the implementation, for the linked implementation of a queue. Pretty straightforward. We don't need to look at the code right now. You can look at that on your own. But any questions about how the linked queue implementation might work? Okay, so let's look at an array-based implementation. And I think what I'm going to do is I'm going to switch over and we're just going to talk about this in Excel. All right, so here we are in Excel. And let's say we're going to have a data member called items, which is going to be an array. And I want to keep it kind of small so that I can illustrate some things without taking too much time. But let's make it 6. How's that? Okay, and so we'll have indices up here, 0, 1, 2, 3, 4, 5. All right, so I think what I want to do is I want to start by showing you a queue that has one item in it. And once we get to play with things a little bit, then we'll start talking about how it would look if there were 0 items in it. But if there's one item in it, let's say we just added our first item to the queue, we'll put in a 13. In addition to our items data member, we're also going to have a data member named front, which is going to be the index of the front item. So that will be 0 at this point. And then we're going to have an index of the back item, which at this point will also be 0. Okay, so hopefully this is easy. I shouldn't say easy. Hopefully you can see how this would translate into an actual class with data members, right? This class has 3 data members, and 2 ints, one named front, one named back, and then one that's an array of ints called items, where the actual contents of the queue are stored. Okay, so let's just do some adding and some pushing and popping of elements to see some issues that may come up. So let's say we want to push 14 onto the queue. So we're pushing it onto the back of the queue. So I would put a 14 here. Whoops, 14. And so notice I'm putting it at back +1, right? Or we could say, the other way to look at it would be, I'm going to increment back, and then I'm going to put the new item at items sub back, right? So items sub back gets new item, something like that. Oops. Okay. Any questions about that? Okay, so let's say I add another one. Let's say I add a 15. So I'm going to increment back. And I'm going to put 15 at items sub back. And then let's say that I pop an item from the array. By the way, I didn't put anything in these elements back here. That probably was bad. I think I should just put something back here just to remind us that array elements are never actually empty, right? There's always some sort of data in there. But right now, what I have here is a picture of the queue 13, 14, 15. That makes sense. How do I know that the 67 is not in the queue?
Because back tells you what the last element is.
Correct. Right. So right now, the contents of our queue, starting from front going to back, are 13, 14, 15. So the way that pop works is simply nothing else, nothing other than just front plus plus. Right? So now this means that 14 is the front element, 15 is the back element. There are two items in our queue. Okay, let's add another item to our queue. So I'm going to set back equal to 3. And then items sub back gets the new item. And let's add another item. So back plus plus. And then item sub back gets 17. And then let's pop. So right now, what are the contents of my queue? So front is 1. Right, front is 1. Back is 4. So the queue is 14, 15, 16, 17. Right. So let's pop. So pop just means make front equal to 2, right? So now the queue is just 15, 16, 17. Let's pop again. So now the queue is just 16, 17, right? So let's go ahead and do another push. So back becomes 5. Item sub 5 becomes the next item that we're pushing into the queue. Now what happens if I want to push something onto my queue? Got a problem, right? Is the problem that I don't have room in my array? The problem isn't that there's not room in the array, right? There's plenty of room up here. The problem is that my queue has done what we call drifting to the right in the array. So now I'm at the end of the array and I can't add anything to the queue. So that's the big kind of problem that arises when you use an array implementation of a queue. There's really, I mean, one possible solution would be, oh, I got the queue has drifted towards the end of the array, so I should stop now and shift everything back down to the front of the array. The problem with that is that's extremely inefficient, right? Every time we get to the end of the array, we have to shift the whole contents of the array down, which is a big O-N operation. That makes our queue really inefficient. So the solution that is the best solution is that if we get into this situation where we've got 3 items in the queue, 16, 17, 18, and I want to push another item in the queue, I just go around and I push it into the front of the array. So the Q then, so if I push a 19, what I'm going to do is instead of incrementing back, I'm going to set back to 0. And I'm going to put the 19 here. So this picture that you see here is the way we would represent the Q 16, 17, 18, 19. Okay, so it might feel a little weird at first, but you can always just go to wherever the front of the queue is, and then you can get to the next item in the queue by adding 1, and you can get to the next item in the queue by adding 1 until you get to the end of the queue. And then if you want to find the next item in the queue after that one, you go to the beginning of the array. Okay. In the textbook, the diagrams that he uses are actually circles, right? He draws a picture of the array as if it was a circle. To be honest, for me, and maybe this is just a difference in how people's brains work, but when I look at the circle and I try to think of that as being an array, it does not help me at all. It helps me more to actually see it like this and just remember, okay, here's the front of the queue, 16, and the queue goes 16, 17, 18, 19. Okay. Maybe I can just show you the pictures from the book real quick and you can tell me if you like them or not. So here's a picture of a circular queue. Here's index 0. Here's index, that would be 7 since there's 8 items in the queue. Front, so this queue is 2, 4, 1, 7. And then you can see some more diagrams. We call DQ or pop, and that just incremented front. We call DQ again, that increments front again, so now the queue is 1, 7. NQ or push a 9, and that puts the 9 here in the 4. So I guess what this illustration does is it shows you that once you get up to the last element in the array, which would be this one here, max Q minus 1, and then you want to push something onto the queue, it's going to go in index 0. Okay, so if you like the circular diagram, feel free to go study that in the textbook. I think for our purposes, I'm going to just stick with the usual array diagram. Since it works, that's what works for me. So, okay, we still have some issues. So what that means is that instead of item sub back gets new item, and so what I had going was I had back plus plus. So when I want to NQ something, when I want to push something onto the queue, back plus plus, and item sub back gets new item. So I need to adjust this slightly, right? Instead of back plus plus, I want to say something like if back is less than array size minus 1, back plus plus, else else back gets 0. Turns out that there's an easy way to say that using modulus, right? We're just going to say back gets back plus 1 modulus, whatever, maybe capacity, right? I mean, I'm not being real formal with the code here. This is more just to try to give you the idea of the concept. Does this make sense? This line right here, if this is confusing, and this is one of the points, I've done this enough times now to know that this is one of the points where students start going, what? But just think of this as the same thing as saying, if back is less than capacity minus 1, just increment it. But if back is equal to capacity minus 1, I can't increment it because then I would be out of index out of range. So I'm going to set it back to 0. All right. So just, to spell that out the long way, it would be something like if back is less than capacity minus 1, back else back gets 0. Okay, so hopefully, maybe not right now instantly, but if you stare at this for a while, you can convince yourself that this big, ugly if statement is just another way of saying back gets back plus 1 modulus capacity. All right, then we're going to do something similar. I mean, the same thing can happen with front, right? So let's keep going. Let's say, let's push one more item into the queue. So back is going to become 1. And I'm pushing a 20 right here. Okay, so hopefully at this point, you can look at this picture and you can tell me what the contents of the queue are, right? Front is 3. So the contents of this queue are 16, 17, 18, 19, 20, because back is 1. Okay. All right, now let's pop a couple things. So I'm going to pop the 16 off the queue by making front 4. I'm going to pop the 17 off the queue by making front 5. Let's push something else now. So I'm going to say increment back, because that's what I do when I'm pushing things. Increment back, and then item sub back gets the next item. Okay, so now I want to pop again. I'm going to pop the 18 off the queue, right? Because right now the 18 is at the front of the queue. So if I call pop right now, what happens to the value of front? Same thing that we did with back, right? Instead of setting front equal to 6, which would be an error, I'm going to set front equal to 0. So my pop algorithm is going to be basically something like front gets front plus 1 modulus capacity. Just same thing as what we did with back, okay? So if I call pop right now, what's going to happen is front becomes 0. Okay? All right. Right, so we have one more situation we need to talk about, but before we go there, anybody want to ask a question so far? All right, so let's play around a little more. I'm going to push 22 onto the queue. Actually, I don't want to do this with front at 0, so I'm going to pop twice. So front's going to become 2. And then I apologize for this, but I'm going to have to push a bunch of stuff now. So I'm going to change back to 4 and push a 23. And then I'm going to increment back and push a 24. And then I'm going to increment back again so it goes to 0 and push a 25. And then I'm going to increment back again, and I'm going to push a 26. All right, what's the situation now? We have a full queue, right? Everyone see that? Front is 2, back is 1. So there's when they're 1 apart like this, that means there's no more room for any more elements. That makes sense to everyone? Front is 2, So the queue consists of 21, 22, 23, 24, 25, 26. Our queue is full. At this point, if assuming that we are using a non-dynamic array, we would, if the client called push, we would just have to throw an error or something, right? Your assignment, much like it was with stacks, is going to be to turn this into a dynamic array. And so we'll double the size and copy it and all that. One little problem though. And so this is the number. So I think I said the first big problem when using an array to implement the queue is what to do about rightward drift. And so we decided the solution to that was to use a circular array. Second big problem is once we've decided to use a circular array, this situation where front is one more than back could mean that the queue is full, but it could also mean that the queue is empty. You have the same situation if the queue is empty. For example, right now, if I were to pop 6 times, what would happen? Front would go 3, 4, 5, 0, 1, 2. And then I would have an empty queue, but the picture would be exactly the same. So, got to figure out what to do about that. We got to have some way to tell the difference between if the queue. So the situation is if front is one more than back, that means that the queue is either full or empty, and we don't know which one. So a couple different ways to solve that problem. The common way and the way that we're going to actually use, I'm going to save it for last, right, because it's the best. But one solution would be just add another data member called is full. Start it off equal to false. Then if you push, and as a result of the push, you end up with this situation, you know, change it to true, right? And then if you ever pop, no matter what, you can always just make sure that it's false, right? So then that just means that if you have the situation where front is one more than back and push is called, you can just say, okay, is the queue full? If it's not, go ahead and push. Go ahead and do the push. If it is full, then throw the error or whatever it is you're going to do. So that's one technique. Another technique is that you always you separate the front and the back of the queue by one. You never allow this situation to happen. So if I call push and back is 2 less than front, then I say, sorry, can't do that. I'm not going to push if that push is going to require that I use every element in the array. So that's just another technique. I find that one to be a little bit awkward because then it gets a little confusing because, well, the way that you end up having to do it is back ends up being the index of one element past the back of the queue. Anyway, I'm just throwing that solution out there just so that it's sort of in the back of your mind, you're aware that there's another possible way to handle this. What we're going to do, and what I think is sort of the classical solution to the problem, is we're just going to have a num items data member. And so we can just check to see if num items is equal to capacity, then that tells us that the queue is full. If num items is 0, that tells us that the queue is empty. Okay? Any questions about that? Let's go and at least take a quick look at the actual code. I think I will go to just take a look at the assignment, and I will share that in a second. Um, share. Oh, I don't have it in the menu yet, but it's actually there in the website. I just have to update the menu. Okay, so this is very similar to what you did with the stacks. Um, your, your class should double the size of the array when an attempt is made to enqueue an item when the capacity is full. Your class should half the size of the array when an item is dequeued if it causes the number of items to be half the capacity or less. So apparently we are going with enqueue and dequeue instead of push and pop. So here's the code. You'll see I've got my default capacity. And then I've got my items. I've got my front. I've got my back. And I've got my num items. You guys are looking at this, right? I shared this.
Yes, it's
okay.
We can see it.
Usually there's like a glowing outline around what I'm sharing, but it's not for some reason. So that's the header file, and you can see the enqueue, dequeue, peek front. So I basically stuck with the names of the functions that the textbook was using. Let's just look over the code a little bit. Oh, that's what I forgot to talk about is how do we start off the queue being empty? So hopefully it will make sense. We're going to set front to 0 and we're going to set back to, so in the case of our Excel spreadsheet example, there were 6 items. So back would be equal to 5. And that's going, because num items is equal to 0, I know that that indicates an empty queue. Let's just take a look at that again real quick. Okay, so what I had said is that if front is 1 more than back, then it's either an empty queue or a full queue. So the question is, okay, well, how do I get started? When I first declare the queue, what do I want front and back to be? I mean, I suppose I could let them be 2 and 1 and everything would work fine, right? Because it's a circular queue, it doesn't really matter where we start. But it kind of makes sense to have front be 0, right? And if front is 0, what's 1 less than front? Well, it would be 5. Makes sense why it would be 5. I will take that as a yes. Oh, I did get a yes. Okay. There's something weird going on with my sharing. Oh, there we go. Okay, you guys are looking at the code again, right?
Yep.
Okay, so front gets 0, back gets default capacity -1, num items get 0. That's the constructor. Is empty, we just check the value of num items. Enqueue, in this version of enqueue, we're just returning false if the array wasn't big enough. So we say if num items is less than default capacity, here's my back gets back +1 modulus default capacity. Items of back gets a new entry. Num items ++. Result gets true. Return the result. Okay. We could also just, this is obviously, I can tell this is from the textbook. If we were doing this, we would probably just say return true right here, right? And return false. right here. But either way. Any questions about NQ? So then DQ is just if not empty, and here's my front gets front plus one modulus default capacity. That's what I typed in the Excel spreadsheet. I also have to subtract one from num items and then set result to true. All right. Any questions about the code, what's going on there? I do realize sometimes it's hard to just have code thrown on the screen and expect you to understand it right away. So
Yeah, the more code, the better.
the more code, the better.
Always. Well, no, not always.
Yeah,
but
yeah.
you know what I'm saying.
I know what you mean. Yes, yes. Okay, I think that I am done talking about Q implementations, unless there are some questions. In the textbook, he follows this up with like a very, very, very short section on implementing a priority queue. I'm not too worried about that because what's going to happen is we're going to discover in a couple chapters a much better way of implementing a priority queue. So, you know, you will need to just read through that section quickly so you're ready for, you know, if a quiz question comes up about it or something. But we will hopefully get there. Oops, I'm trying to remember. So yeah, actually, anyway, yeah, I'm hoping that we'll be able to get there if there's no more canceled classes or anything like that. Okay, let's go back and look at the assignment a little bit. So I wanted to look at the second part of the assignment. This assignment, 11.2, actually has nothing to do with queues. I just wanted to get this assignment in somewhere, and this week the programming is actually pretty light, as is the reading. So I decided this would be a good week to do it. And basically what I'm having you do is I'm having you rewrite your sequence class. That's supposed to sound ominous, but
That did sound ominous.
okay. It turns out that this way of writing it is much, I hate using the word easier. I'll use the much less tedious. We're going to do it without pointers. We're going to just use stacks. Okay. So we're going to declare, and so the thing I like about this assignment, the reason I didn't want to just skip it, is that it really tests to see if you understand, I'm reading from down here in case you missed it, the separation of specification from implementation. In your sequence class, from the specification level, you have things like a current, a current and a, you don't have a pre, from the specification perspective, right? You just have a current item. That's the word I was trying to think of. From the implementation perspective, you have a cursor and a precursor, which are pointers, right? And you also have a head pointer and a tail pointer and all that. What we're going to do here is we're going to implement sequence again, but we're not going to have any pointers, no linked lists, no cursor, no head pointer, no tail pointer, none of that. We're just going to focus on meeting the requirements of the specification, but doing it using stacks instead. Okay, and so I guess I could talk a little bit about what that's going to look like. So let's read here. there will be exactly 2 data members, both STL stacks, named stack 1 and stack 2. The bottom of stack 1 is the beginning of the sequence. The elements of the sequence continue up to the top of stack 1. The next element of the sequence after the top of stack 1 is the top of stack 2. The elements of the sequence then continue down to the bottom of stack 2, which is the end of the sequence. And then if there's a current element, that element is at the top of stack 1. Okay? So kind of a bizarre way of doing it. Bizarre, but fun, I guess I would have to say. So let's talk about that a little bit. What if I have a stack with the numbers, I'm just going to do it in order. I'm sorry, not stack, I meant to say sequence. What if these are the numbers in my sequence? And what if 5 is the current item in the sequence? Okay, so I'm talking about this from the specification perspective, right? I'm not talking about how it's being implemented at all. I'm just saying here's a sequence and 5 is the current item. So what I want to do is, how would I draw this given, oh, I just realized you guys aren't seeing what I'm typing here. Let me do this. You can see now, right?
Yep.
So here's my 7 items in my sequence, 1, 2, 3, 4, 5, 6, 7. 1 being the first item in the sequence, 7 being the last item in the sequence. 5 is the current item. So I want to talk about how we would use this arrangement to represent that sequence. So it says that the bottom of stack 1 is the beginning of the sequence. So I know the 1, let's say I've got, a stack here and a stack here. This is stack 1. This is stack 2. So I know that the bottom of stack 1 is going to be the 1, right? And then the instructions say that the items in the sequence continue on up stack 1, right? The elements of the sequence continue up to the top of stack 1. So 1, 2, 3, 4, 5, 6, 7. Let's actually, just for fun, let's say there's a couple more here. Okay. And then after I get to the top of stack 1, what happens? The next element of the sequence is then the top of stack 2. So 8 would go here and then on down. And so the last item in the sequence is the bottom of stack 2. All right. So hopefully you can look at this and you can see, okay, this is a picture of the sequence 1, 2, 3, 4, 5, 6, 7, 8, 9. Except for one thing, right? We have not taken care of the fact that 5 is the current item. How does the assignment say we're going to specify the current item? If there is a current item, which there is, then that element is at the top of stack 1. Okay, so we haven't really done that correctly, right? We need the 5 here to be at the top of stack 1. So how are we going to rearrange this so that the 5 is at the top of stack 1, but we still have the sequence in the right order? The answer is we're going to have to shift the 6 and the 7 over to stack 2, right? So stack 2 is going to be 6, 7, 8, 9. And stack 1 is going to look like this. So now we've got the sequence 1, 2, 3, 4, 5, 6, 7, 8, 9. 5 is the top element in stack 1, so it's the current item. So this is an accurate picture of how this abstract situation is going to be implemented. Anybody want to ask a question about that? So you're going to have to write functions like advance and start, things like that, right? And so basically the idea is, so if I, let's talk about advance just as one example. I don't want to do the whole assignment for you, but just as one example, advance. Advance means take the current item and move it to the next item in the sequence, which would be the 6. So how do we maintain the exact same sequence, except we make it so that the 6 is the current item instead of the 5? Well, we got to get the 6 over here on this side and get rid of it from there. Right? Okay. Hopefully that made sense. But, right, everyone is typing correct stuff. What if I say start? That means that the 1 has to be the current item, right? Can I do that? Can I make 1 the current item? Well, right, I'm gonna just have to move all of these numbers, 6, 5, 4, 3, 2, from stack 1 over to stack 2 to make it so that the picture here of the implementation accurately represents this abstract situation, right? All right, sounds like you guys are getting it. I'm going to stop there talking about it unless someone has some questions or just wants me to babble on a little longer. Open to requests. If you start working on the assignment, on this assignment, and you start thinking anything at all about pointers or cursor or precursor or any of that stuff, then just stop yourself because you're going down the wrong path.
If you could be a planet, which planet would you be?
I have no idea. All right. Yeah, I actually really enjoyed writing this the first time I did it. It was really fun. And I also think that it's a good test to see whether you're getting the point of the stuff we're doing. All right, that's all I have planned for today. I think on Thursday, we will be starting on trees. So unless anyone has a question, I will see you all on Thursday.
Thanks, Dave.
See you.
All right.
Thanks.
Thanks.
That was
I
a
just
long one.
wanted to remind you that you were going to post the recording.
Thank you. Yes, I will post the videos. Thank you for reminding me.
Thank you.
All right. See you Thursday.